Swayam Prabha. Digital India. Educated India.
So if we look at this equation, case 1, if my xi is lambda r, then d xi by dr is lambda, then dr by d small r is dr by d xi into lambda, and d2r by dr square is equal to d2r by d xi square lambda square. Okay, so now if we look at this with a plus, okay, let's do that here. I get d2r dr square, which is d2r by d xi square lambda square plus 1 over r, okay, is lambda over xi dr is dr by d xi into lambda, okay, plus lambda square minus k square by r square is lambda square by xi square into r equal to 0. So you can see that lambda square features everywhere. So lambda square goes from here, and from here, so that I get d2r by d xi square plus 1 by xi dr by d xi plus 1 minus k square by xi square into r equal to 0. That is case 1. Okay. Case 2. Case 2 is xi is equal to j lambda r, which means d xi by dr is equal to j lambda. Then d capital R by d small r is d capital R by d xi into j lambda, and d2r by dr square is d2r by d xi squared into j lambda whole squared. Okay. Now if we look at this equation again, d2r by dr square is minus lambda square d2r by d xi square. Then we have 1 over r is equal to j lambda by xi. Then dr is dr by d xi j lambda, okay, plus minus lambda square minus k square by r square. Okay, r square is j lambda square by xi square. Okay, so that into r, that is equal to 0. So I get a minus lambda square here. I get a minus lambda square here. Okay. If I take this minus lambda square out, Okay, then I get a 1 minus k square by xi square into r, because I have a minus and a minus, I have a plus. Okay, so if I cancel out all the minus lambda squares, I get the same equation. Okay, so that is Bessel's equation. Okay, so what does it say? Let me copy it here. The equation looks like d2r by d xi square plus 1 by xi dr by d xi plus 1 minus k square by xi square into r is equal to 0. This is Bessel's equation, and its solutions are, for xi of the form lambda r, you get a j k lambda r and yk of lambda r. Okay, these are cylindrical Bessel functions of the first and the second kind of kth order. Okay, and for xi equal to j lambda r, you get ik of lambda r and kk of lambda r. Okay, and these are modified Bessel's functions of the first and second kind. Okay, and we said when the plate is closed in the theta direction, then k is an integer n, and therefore the total solution of R is a linear sum of all these solutions, which is C j n of lambda r plus d I n of lambda r plus e y n of lambda r and f k n of lambda r. Okay, so now what happens? The yn and the kn are singular, that means they blow up. They are singular, they go to infinity if r is equal to 0. So that means in the plate, if the origin is included, the plate includes the origin, it is not some annular region. Okay, it's not an annular plate, then yn and kn blow up, which means, okay, from a realistic engineering standpoint, E and F have to be 0. Okay, now please don't confuse that this is a number which becomes n, okay, so that is the number k which became n, whereas this k is the Bessel function name, just as j, y and ik, okay, so please don't confuse. So this, okay, that k as it became integer, it brings about the order over here, order number here, okay, for various k values, okay. So now, so therefore we will now look at a case where we have a circular plate, okay, it is closed in the theta direction, which means k must be an integer n, and origin is included, origin is part of the domain, okay. So as a result, my solution is c times j n of lambda r plus d times I n of lambda r is r of r. That is the solution, okay. Now, so we look at one particular case, okay, we look at a clamped, okay, circular plate. And what does clamping mean? Clamping means the u3 at r equal to a for all theta for all time is 0, okay, and this amounts to the r equal to a being 0. Then the slope del u3 by del r at r equal to a comma theta for all time is equal to 0, which means dr by d small r at r equal to a is equal to 0, okay. So if we subject this to these two conditions, we get two equations. We get Jn of lambda a, In of lambda a, djn dr lambda a, din dr of lambda a, c d equal to 0. So again, for non-trivial values of c and d, if this 0 has to hold, then the determinant of this matrix must be 0, determinant of that matrix must be 0. That means Jn lambda a minus din by dr lambda a minus djn by dr, what is the product, this into this minus this into this, so djn dr lambda a into in lambda a must be equal to 0, okay. So now this is satisfied by many lambda a's, many values of lambda a will satisfy this equation, okay. So let's call them the m mth order. So lambda a, the m values, m, let's say going from 0, 1, 2, okay, satisfy the equation, satisfy. And therefore, if we now remember lambda fourth as rho h omega square by d, okay, which means now my omega square is equal to lambda fourth d by rho h, and omega is equal to lambda square root of d by rho h, okay. Then if lambda a are paired together and I get the m values, this can be written as the lambda a m, okay, and already there is an n index because there is k has taken integer values, so we will put an n index also, that square by a square, because we have only lambda square here, square root of d by rho h, okay, and so this becomes omega mn. For every k equal to n, there are a set of lambda a values. So the lambda a come with the n index hidden, okay. So once I have lambda square, I write it as lambda a squared with index mn, but I remove the a in the denominator, okay. Now we don't like to keep derivatives in our equations, so we use identities, okay. So we have derivatives over here which we don't like, okay. So what we will do is we use identities which are a djn lambda a by dr, that can be written as n jn lambda a minus lambda a j of the n plus 1th order lambda a, then a times din by dr lambda a is equal to n in lambda a plus lambda a I to the power n plus 1 into lambda a, okay. So if this, the derivatives are replaced by this, what we get is now an equation jn of lambda a I n plus 1 lambda a plus I n lambda a j n plus 1 lambda a equal to 0, okay. Now once we found the lambda a of the mth value, if we go back and put it in here, then the matrix becomes singular, so that any one equation is valid, okay. Only one equation is unique over here, so we get jn lambda a c plus I n lambda a d equal to 0. So this is what I mean by one of these being solved in terms of the other. So we will solve d in terms of c, okay. So d is minus Cjn by In. Okay, so this d now is minus Cjn lambda a by In lambda a. Okay, so now if we write it up, what do we get? We get u r theta, which we had written as r of r into theta of theta. Okay, so that becomes now equal to c times jn of lambda r minus jn of lambda a by In of lambda a into In of lambda r, okay, into a cos n theta plus b sin n theta, or we can write this as cos n theta minus phi. Okay, so this becomes equal to c times jn lambda r minus jn lambda a by In of lambda a In of lambda r cos n theta minus phi. Okay, so that's the mode shape, again unknown to the extent of one constant. Okay, so those now this is a mode shape, this is a mode shape r comma. Okay, so we have found the mode shape and the corresponding natural frequency. Okay, now one thing is that unless the forcing is decided, unless the force is decided, okay, which way the mode will be oriented is not known, will not be known. Okay, just as a mode shape, how a mode will be oriented will not be known, whether, you know, if a mode has two nodal lines, whether they will be like this or whether they will be a little more rotated, you know, will not be known. Okay, only when there is a forcing, okay, in accordance with the forcing, the exact phi will be made clear. Okay, so we now have the mode shapes for a circular clamped plate. I will close the lecture here. In the coming class, I will start by showing the animations for this plate, circular plate. Okay, thank you. I will close the lecture here.